So today let us discuss about mechanism of pressure development in an oil film. So I told that hydrodynamic bearings are the bearings where due to the rotation of the shaft itself automatically the pressure is generated in the oil film present between journal and the bearing. So between the journal and the bearing there will be clearance, no? And that clearance will be completely filled by oil in a hydrodynamic journal bearing, because that journal bearing is completely immersed in oil, or else the journal bearing will be completely closed and into that cavity the oil will be filled, lubricating oil will be filled. And when the lubricating oil is filled, due to rotation of the shaft, the pressure will be generated after a certain speed. Until the shaft reaches certain speed, there will not be any pressure development. After a certain speed is reached, then the pressure will be generated in the oil film, and that pressure will be sufficient to make the shaft float in the bearing. So there will not be any metal to metal contact. This is the principle of operation of a hydrodynamic journal bearing. So how the pressure is generated in the hydrodynamic journal bearing, that we will be studying here. Okay? What is the mechanism by which the pressure is generated inside a hydrodynamic journal, that we will be studying here. So you observe this figure. Let us consider that AB is a stationary plane and A dash B dash is a moving plane. Means what? AB represents our bearing. Okay? So actually bearing will be circular in shape, and bearing and shaft will be circular in shape. But suppose I take a small length of the bearing and shaft, then what happens? It can resemble as a straight line. Or else if suppose you open the bearing and make it straight, it may look like this. So here what happens? When the shaft is rotating inside the bearing, there a inclined plane will be formed between the shaft and the bearing. This is the bearing plane, and this upper one is the shaft plane. That is the plane which is moving. When the shaft starts rotating, this plane will start moving relative to this stationary plane, that is bearing. Okay, and both the surfaces will not be parallel to each other. They will be inclined to each other. They will be inclined to each other by an angle, let us say as alpha. Alpha is the angle between the two planes, that is one moving plane and another one is stationary plane, that is between the bearing surface and the between the shaft surface and the bearing surface. Then if suppose the shaft is moving with a velocity of say u, a linear velocity u is equal to what? Pi d n by 60. Suppose n is the rpm of the shaft, then velocity of the shaft u is pi d n by 60, where d is diameter of the shaft. Okay, so upper plane will be moving with a velocity of say u, that is the shaft is moving with a velocity u, and lower plane is stationary, that is the bearing is stationary. So velocity is 0 at a and velocity is equal to u at a dash. Okay, so the velocity is here a and here it is a dash c dash. Okay, so this represents the velocity curve. AC dash represents the velocity curve at the left end, and BD dash represents the velocity curve at the right end. Okay. So consider the case of two non-parallel planes. These are two non-parallel planes because this plane is inclined at an angle of alpha with this plane. Okay. So this resembles the journal surface, that is the shaft surface, and this resembles the bearing surface. So bearing is stationary while the journal or the shaft is moving. The width of the plane in the direction perpendicular to this direction, okay, perpendicular to this plane, the width is considered as unity. Okay, width is very large. It is assumed that the width of the bearing perpendicular to this plane is very large, means in it's this direction, in in the perpendicular direction, the width of the bearing is very large. Hence let us consider that a unit width of the bearing. Okay. Hence, as the width is considered to be very, very large in the perpendicular direction, so it is assumed that there is no flow of lubricant in the perpendicular direction. You have to assume that lubricant is flowing from left end to right end. There is no flow of lubricant in the perpendicular direction, that is in the perpendicular to this plane. Okay? That is the assumption you have to make, because there will be very negligible amount of liquid will be flowing, lubricant will be flowing in the perpendicular direction. Now let us consider the flow of lubricant through the rectangular areas. Okay, so A dash is a rectangular area. Here it will be flowing inside, and here B dash is also a small rectangular area. It will be flowing inside this one. Okay, having a width equal to unity. Let us consider that the width of the rectangle, that is A dash rectangle, in the perpendicular direction is unity. Okay, and similarly B dash also, the width is unity. The volume of the lubricant entering the section A dash during unit time is A C dash A dash. The volume of liquid entering this section in unit time is A C dash A dash. Here the liquid is entering, and from here the liquid is leaving. Okay, and when the liquid is entering here, the volume of the liquid that is entering is equal to A C dash A dash, and volume of the flow liquid which is leaving this is equal to and the volume of the fluid which is leaving this section, that is B dash, is equal to B D dash B dash. And you can see here that A C dash A dash is larger than B D dash B dash. No, means what? Volume of fluid entering is more than the volume of fluid leaving. And when the volume of fluid entering is more and volume of fluid leaving is less, then automatically pressure will be built up, no, in the mid section. Because volume of fluid entering is A C dash A dash, and volume of fluid leaving is B D dash B dash. Okay. Hence, as more quantity of fluid is entering and less quantity of fluid is leaving, due to that what happens? The more amount of liquid gets filled inside this surface, and due to that there will be pressure built up in this region. Okay, and that pressure will be built up, and as we are assuming that the fluid is incompressible, whatever the lubricant oil we are using, it is assumed to be incompressible fluid. And when the fluid is incompressible, then what happens? Automatically pressure start building in this region. And also you know that there is no, we have assumed that there is no flow in the perpendicular direction, perpendicular to this plane. Hence fluid gets accumulated in this region. Therefore, the excess volume of oil carried into the space is squeezed out through the section A dash and B dash. Means what? Excess liquid is there, it will be pushed out through A dash and B dash, producing a constant pressure induced flow through these sections. So it produces a constant pressure induced flow. Due to the pressure of the fluid starts flowing in this direction and also in this direction. Due to this flow of fluid is called as pressure induced flow. So if you draw the velocity distribution for this pressure induced flow, it will be A dash like this curve, and at B dash it will be like this, and This is the velocity curve due to flow of fluid, due to rotation of the shaft, and this is the velocity distribution due to pressure induced flow. And if you overlap, superimpose this flow on this flow, superimpose this curve on this curve, then we will get this type of curve. Yeah. So this is also velocity distribution. This is also velocity distribution. This is velocity distribution due to moving shaft, that is rotation of the shaft or flow of the fluid. And this is the velocity distribution due to pressure buildup. And when the pressure is built up, the oil is pushed outward from here and here. And that is called as pressure induced flow. And the velocity distribution will be like this on both sides. If you superimpose this curve on this curve, we'll get this curve. A C dash, A dash here. And here we'll be getting this curve. Because you see here that this is on negative side and this is on positive side. So this much amount of area should be removed from this curve. And this is positive side and this is also positive side. So this much amount of area gets added to this curve. So see here that B D dash B dash. So here the area is more, here the area is less, and whereas here it will be exactly straight line. Okay. Velocity will be exactly straight line, and here the velocity will be gradually increasing. That is more. Okay. Here what happens, due to whatever the pressure buildup is there, the pressure will be maximum at the section J dash. Here the pressure will be very, very high. You see here that this is pressure distribution curve. A dash, N, B dash. This is called as pressure curve. If you plot the pressure, if you measure the pressure inside this bearing and plot it, you will get this type of curve. And the pressure is not maximum exactly at the center of these two sections. It will be somewhat nearer to BB dash. See here, the curve is not exactly symmetrical. Here this point N is nearer to BB dash. And as there is no pressure into induced flow in J dash, therefore the velocity curve at J dash, that is JK dash, is a straight line. Here there is a pressure induced flow and here there is a pressure induced flow. So here it has become curved. Here negative area, here positive area, but here it will be exactly equal to the this one. Okay. The area of triangle J K dash J dash, this triangle J K dash J dash is exactly equal to the areas A H C dash A dash. This area will be equal to this area, and also this area B I D dash B dash. This area is also equal to J K dash J dash. Okay. See here, area of triangle J K dash J dash is equal to area of triangle A H C dash A dash and B I D dash B dash. This area, this hatched area is exactly equal to this hatched area, which is exactly equal to this hatched area. Okay. The curve A dash N B dash shows the pressure distribution in the oil film. In line LM, this line is called as mean pressure line. LM is the mean pressure line in the mean pressure in the oil film. And W is weight on the shaft. Okay. Hence, due to whatever the pressure is developed inside this bearing, it will be able to support this load capital W on the shaft. Okay. Preventing metal to metal contact between A dash B dash and AB. So like this, the mechanism of pressure development is there in the hydrodynamic bearing. Is there any doubt till this point? Is it clear? Okay. Then let us move on to the Reynolds equation in 2 dimension. In 1866, O. Reynolds first obtained a differential equation giving relationship between the pressure gradient, viscosity of the lubricant, and the form of an oil film. In 1866, Reynolds first obtained the differential equation which is relating between the pressure gradient, that is dP by dx, viscosity of the lubricant, that is mu, and the form of an oil film, that is the shape of an oil film. There are certain assumptions are made in deriving the Reynolds equation. Okay? We'll be deriving Reynolds equation in 2 dimensions because as we are considering that the flow in z direction is 0, that is the flow in perpendicular to this plane is 0. And so we can use Reynolds equation in 2 dimensions. Okay? So these are the assumptions made in deriving the Reynolds equation. Now let us discuss one by one what are the assumptions. Actually, what are the assumptions and what they interfere. Okay. Okay. The main assumptions made in the Reynolds equation are: first one is there is no flow in the direction perpendicular to motion. That is, motion direction is, we are considering this direction, no, the positive x direction, and perpendicular to this motion direction is, that is perpendicular to z direction. It means along z direction, that is perpendicular to this plane. Okay, you can see here. This is x, this is y. Perpendicular to this plane is z. In the z direction, we are assuming that there is no flow in liquid. That is the first assumption. There is no flow in the direction perpendicular to motion. Means what? There is no end leakage from the bearing. There is no end leakage from the bearing. Okay. Then second assumption is that the viscosity of the lubricant is constant throughout the oil film. Okay, means what? Viscosity at this point, everywhere inside the bearing, the viscosity of the oil remains constant. Oil viscosity does not change from point to point. That is the second assumption. Then the third assumption is that the motion of the fluid in the film is laminar. Means what? The flow is laminar. When the lubricant oil is flowing, it will be flowing in a laminar profile. That is plate like straight lines. You have studied no laminar and non-laminar flows in fluid mechanics. Okay, so motion of fluid is laminar. Then fourth one is the inertia forces in the oil film are so small that their influence on the pressure developed in the film may be neglected. Okay, so when the oil is continuously flowing inside the bearing, because of the molecular weight of the oil, that is molecular mass of the oil, the inertia will be built up in the oil. And we are considering that, or we are assuming that the whatever the inertia that is built up in the oil, the inertia forces that are built up in the oil due to flow of oil is very small and it is neglected. Then fifth assumption is that no slip occurs between the lubricant and the bearing surfaces. Means what? Here this is bearing surface and this is shaft surface. Between these two there is a lubricant oil is filled, and here whatever the lubricant oil is there present here, from here to here and from here to here, that oil is in continuous contact with the surfaces. There is no slip between the oil film and the bearing surface. Here, whatever the oil is there, the velocity of the oil near AB is 0, and velocity of the oil near A dash B dash is exactly equal to the velocity of the A dash B dash. That is shaft. That is U. Means what? Velocity of fluid at the shaft is exactly equal to the velocity of the shaft. Velocity of the fluid at the bearing is exactly equal to the velocity of the bearing. There is no slippage between the fluid film and the surfaces. They are in fixed contact between the surface and the lubricating oil. This is the fifth assumption. Then sixth assumption is that fluid is incompressible. Means what? It is a Newtonian fluid and it is an incompressible fluid, because when the, if suppose the fluid is compressible means what? When you apply pressure on the fluid, the volume of the fluid goes on decreasing. If you apply load on the fluid, if the volume of the fluid goes on, compressive load on the fluid, if the volume of the fluid goes on decreasing, then we call that type of fluid as compressible fluid. Here we are assuming that whatever the lubricant oil we are using, it is a incompressible. Means what? If lubricant get accumulated, there will be build-up of the pressure in the bearing. Okay, that is the inference. Then seventh one, that is, it is Newton's law of viscosity. Seventh one is Newton's law of viscosity. Means what? We are assuming that whatever the lubricant oil we are using is a Newtonian fluid. Okay, is a Newtonian fluid. Okay. Then that is shear stress is proportional to the rate of shear, or shear stress is directly proportional to the velocity gradient. This assumption means that the lubricant is a Newtonian liquid or Newtonian fluid. Newtonian fluid means what? The fluid or the liquid which obeys Newton's law of viscosity is called as a Newtonian liquid. Then last assumption is that the clearance between two bearing surfaces is so small that the change in the pressure across the clearance can be neglected. Okay? Means what? Whatever the gap is there, no, between this bearing and the shaft, it is very small that the pressure variation in y direction is neglected. Okay, that is the eighth assumption. Pressure variation is in x direction is considered. Pressure variation in y and z direction are considered to be 0. There is no change in pressure in y and z direction. That is the final or eighth assumption. Okay. So these are the assumptions made in Reynolds equation for